So 4.7 is all about how to do inference for experiments. And so here we go. A completely randomized design. A completely randomized design. What does that sound like? What's that sound like we're going to do? Everything's going to be very structured or random? Yeah, it sounds like everything's going to be pretty random. Most things are going to be a little random. So a completely randomized design can be done with this thing right here. This is called a tree diagram. It's called a tree diagram. It doesn't really look much like a tree, but it's called a tree diagram. And so this is a completely randomized design for the caffeine experiment that we've been talking about. So we had 20 student volunteers. We randomly assign them to 2 different groups, okay? So we've got these 20 student volunteers. We randomly assign them. That's important to the completely randomized design. If we select who goes to which group, it's no longer random. So the random assignment, they go into 2 different groups. One group is going to get the caffeine, the treatment 1. The other group is going to get no caffeine, that's treatment 2. And the sizes of the groups need to be pretty close to the same. And then they're going to say what treatment they get. And then at the end, we're going to compare the response variable. We're going to compare their changes in their pulse rate. This is a completely randomized design. So the definition of completely randomized design is that the experimental units are assigned completely at random. Okay, so we're assigning them completely at random. Random assignment is absolutely essential in any experiment. I don't want to have any chance that I am biasing the experiment. Okay, so I want to make sure that we're having close to the same number of students in each group. It doesn't have to be exact, but I want to have about the same number of people in each group. But I definitely have to randomly assign them to those groups. Again, to create roughly equivalent groups. Okay, so here's our example. What distracts drivers? Is talking on a cell phone while driving more distracting than talking to a passenger? David Strayer and his colleagues at the University of Utah used 48 undergraduate students as subjects in an experiment. The researchers randomly assigned half of the students to drive in a simulator while talking on a cell phone, and the other half to drive in a simulator while talking to a passenger. One response variable was whether or not the driver stopped at a rest area that was specified by researchers before the simulation started. We're going to outline a completely randomized design for this experiment. So basically, we've got 48 students. We need 2 groups, okay? And then we're going to give one the treatment of talking on a cell phone and one the treatment of having passengers in the car. They're in a simulator, so we're not putting people at risk, okay? But at the beginning, basically the researchers say, hey, there's going to be a rest stop, make sure you stop, okay? Now, while they're driving the simulator, they have to be paying attention that the rest stop is coming, and they have to remember that they were supposed to stop. And so that's what they're measuring, is whether or not they stopped at the rest stop. Do you guys understand the experiment? Yeah. Perfect. Draw a completely randomized design for this experiment. Basically, draw that tree diagram, okay? So what should we start with on the far left?
48 undergrads.
All of our 48 students. Very good. There were 48 students at the beginning of the experiment. So we do have 48 students. It is totally fine that they volunteered to be a part of the study, okay? I don't have to always go out and just randomly pick people to be in an experiment. Okay, wouldn't that be weird if someone came up to you and said, hey, guess what? You were just walking by and you have randomly been picked to come out and sit in a simulator for about an hour. Is that cool with you? You don't have nothing else going on, right? That's not the way it works. So we definitely have volunteers. That's totally fine if you have volunteers. What should we do next? Perfect. The next thing is we're going to do random assignment. We're going to have two groups. One group is going to have 24 students. The other group is also going to have 24 students. Randomly assign them. How do we randomly assign them? That's kind of up to you. You can do a hat method. You can do random number generator, whatever, as long as it's random, okay? Again, hoping to balance out that some people who've been driving a little longer are in both groups. Some people who, are better drivers are in both groups. Have any of you ever ridden with that friend and you're like, oh my God, I'm going to die today? Like, you're literally in the car with your friend going, I don't think they can drive. This is not good. And you're like, I should just walk, right? So hopefully we've got a little bit of both of those, a little bit of those people in both groups, those people that just can't drive. All right, what are we going to do with group 1? What should we do now? Yeah, so group 1's going to get a treatment. Group 2's going to get a treatment. Now, it doesn't really matter which one you do, okay? If you want to say that group 1's going to get the passenger, group 2's going to get the cell phone, that doesn't really matter either way. But basically, we're giving each one a treatment. That's the big thing. We're going to give each group a treatment. One of them's going to get the cell phone. One of them's going to get the passenger. And what's our final step of the tree diagram? What's our final thing that we need to do? We're going to bring them back together and we're going to compare whether or not they stopped at the rest stop, okay? Again, I want to compare the response variable, okay? What am I actually looking at, okay? I don't want to compare, what did they talk about? Because I don't care what they talked about. I just want to compare the variable that I'm measuring, and that's whether or not they stopped. Do you guys have any questions about how to make a tree diagram? This seems really easy, right? That's good. All right, cool. So I think we're going to do another one. Look at this. Yeah. We're going to do one more. This time I want you guys to draw the whole thing out. So here's the example. Research has shown that magnetic fields can affect living tissue in humans. To investigate if magnets can be used to help patients with chronic pain, researchers conducted an experiment. A doctor identified a painful site on each of 50 patients and asked him or her to rate the pain on a scale from 0 to 10, mild pain to severe pain. Then the doctor selected a sealed envelope containing a magnet at random from a box with a mixture of active and inactive magnets. The chosen magnet was applied to the site of the pain for 45 minutes. After being treated, each patient was again asked to rate the level of pain from 0 to 10, and the improvement in the pain level was recorded. So go ahead and draw out that tree diagram, and that is going to be your completely randomized design. All right, let's see what you guys got. What do you think? We're going to take these 50 people, and what are we going to do with them? Random assignment. Okay, why are we doing random assignment? Yeah, so we want to make sure that we do things randomly. We don't want any bias here. And what's our little key phrase for random assignment? Create roughly equivalent groups. Very good. Okay, perfect. And then once we randomly assign them, basically what's happening, 25 of them are getting the active magnet, 25 of them are getting the inactive magnet, and we're going to check their pain tolerance. All right, so group 1, we got 25 patients get active, 25 get inactive, and we're comparing their improvements, right? Their pain improvement. All right, how do we do? Do we do okay on this tree diagram? Do you guys have any questions about how to make a tree diagram? Are you sure? Come on, Nate. You don't have any questions? No. Not even one? Perfect. All right. So make sure you always have that random assignment in there. Okay, we got to make sure we got that random assignment to get those roughly equivalent groups. All right, perfect. Why are we doing such detailed experiments? Statistically significant results. In this experiment, the treatments were assigned by having the doctor choose an envelope at random, okay? So we did have random, we even had random treatments given, right? So do you think the doctor knew which envelope had the inactive and active magnets? Probably not. So the doctor didn't even know which ones were active treatments. What is that called when the doctor doesn't know and the patient doesn't know? Double blind. Perfect. So we had a double blind experiment. And again, what is the purpose of the random assignment?
That's what I found.
Hey, I'm talking. There it is. To create two groups of patients who were roughly equivalent at the beginning of the experiment. So again, the purpose of the random assignment is to have two groups of patients who are roughly equivalent at the beginning of the experiment. We don't want to put the people, I don't know, maybe if we said, hey, the older 25 go over here and the younger 25 go over here, and these people are going to get the inactive magnet, these people are going to get the active magnet. What if it had to do more with their age than it did with the magnets, right? So we don't want to introduce the confounding variables. We want to have roughly equivalent groups, some of the old and young in both groups, okay? That's what we want to do. All right, with only 50 patients, it is unlikely that the two groups were exactly equivalent. By chance, it is possible that the active magnet group had a higher proportion of patients who were going to feel better anyway, okay? Maybe the placebo effect was really working on them. I don't know. So here's the deal. This means that the average improvement for the active magnet group might be greater just by chance. So we have to see how much was the difference. Before making any firm conclusions, we have to account for the possibility of chance in all of this experimenting, okay? So we have to make sure that the differences in the response, for the groups in an experiment is larger than what we would expect simply due to chance. This is how I know something is statistically significant. If the results are truly not due to chance, it just happened to happen, okay? That's how you know something is statistically significant. So here is your definition for statistical significance, which I think I forgot to put on here. Oh, no, there it is. So it's on the top of the next page. When an observed difference between the groups is so large that it is unlikely to be explained by chance, then you have statistical significance, okay? If I tell you guys that on average, students get a 90 in my class, okay? And you end up getting a 91. Does that tell you, was that a very big difference? No, not really. So chances are that was just, not that big of a difference. I really don't know if you made a difference or if you just kind of are just as average as everyone else. But if you got a 100 in my class when everyone else is getting about a 90, is that a big difference? Did you do something different, or did it just by chance you got a 100? Probably you did something different. So a big difference means that there was probably something that made a difference, and it could be the treatment. That's how you know something is statistically significant, okay? So, for example, this is the magnet experiment. These are the people that got the active treatment. They had a difference in their improvement of 5.24. Basically, think about on a scale of 0 to 10, how much do you hurt, right? And they say, I'm hurting like a 10. but then they do the magnet thing. How much are you hurting? 5. Okay, and then we average all 25 people. There was an average difference of about 5.24 for the people who got the real magnets. For the people who got the fake magnets, there was only a difference of 1. Do you guys think that there's enough of a difference between these two groups that the magnets really made a difference? Or is this difference just due to chance? What do you think? Is there an actual difference here? Or is this just, maybe it was the magnets, maybe it was something else? What do y'all think? Is there a big enough difference here for you to think that the magnets actually did something? Probably, okay? So here's what we can do, you guys. We can look at their actual difference. There was a difference of 4.14, so that's just subtracting those two. And what we can do is we can see, is this too large to occur simply due to chance? Is this difference too large to occur simply due to chance? Is a difference of 4.14 big enough to say that the magnets really made the difference? Or could this have just been the people that were in the magnet groups just would have felt better anyway? So to do that, what we're going to do in just a minute is we're going to do a simulation to see if there was really a difference, okay? But again, statistical significance. If you have statistically significant results, that means you don't think chance could have been the reason. If it's not statistically significant, you think, well, maybe something else happened, a confounding variable. So here's an example just to think about that for a second. The Physicians' Health Study randomly assigned nearly 22,000 doctors to take aspirin or a placebo every odd-numbered day, hoping to find that aspirin helps prevent heart attacks. These doctors were also randomly assigned to take beta-carotene or a placebo every even-numbered day, hoping to find that beta-carotene helps prevent cancer. Okay? So here's our first question. The proportion of doctors taking aspirin who had a heart attack was smaller than the proportion of doctors taking a placebo who had a heart attack. And the difference was statistically significant. What does that mean, that the difference was statistically significant? That means that the results could not have been by chance. That's all that means. So the difference means that it was large enough that it is unlikely due to chance. The difference was large enough that it is unlikely to be explained by chance. Basically, what's highlighted is the most important part. The difference was so large that it was unlikely to be by chance. Sounds like the aspirin made a difference. The difference was so large, could not have just been a fluke, basically. It really happened. Okay? Part B says, the difference in the proportion of doctors taking beta-carotene who developed cancer and the proportion of doctors taking a placebo who developed cancer was not statistically significant. What does that mean? Could the results have been by chance on this one? Very good. That's basically what this means. This means that the difference was small enough that it could be explained by chance. Again, you get a 90 or a 91, probably you didn't do much different than everyone else. Then your 91, the fact that you got something higher was maybe just by chance. But if you get 100, you probably did something. There's a big enough difference that you probably made an impact in your grade. Does this make sense? Statistically significant, means that there was actually something that made a difference, could not have been by chance, not statistically significant. Maybe chance was just the reason for the small difference that occurred. All right, cool. So remember the simulation? We've got Mr. Luckow's class experiment with the caffeine or no caffeine and whether that's affecting their pulse rate, okay? So, Royce, are you ready? I'm ready. Let's go. Let's lock it in. All right, I'm going to get out of here in 10 minutes. You can talk the rest of the time. Here we go. Assuming that caffeine has no effect on pulse rate, we have this dot plot here that shows a simulation of, like, let's pretend we do this experiment 100 times in this classroom, okay? So the dot plot shows the difference in the change in their pulse rate. So what would a zero mean? What would a difference of zero mean? There was no change in their pulse rate. So before they drank the caffeine and after they drank caffeine, there was no difference in their pulse rate. What would a difference of 1 be? What does that mean? Yeah, a whole big difference of 1 heartbeat a minute. Okay, all right. Is that a big difference? I don't know. Probably not. But there's obviously a difference on this side of your pulse rate is getting higher, okay? So if we do this simulated 100 different times, there were 19 times that the simulation showed a difference of 1.2 or greater. 19 out of 100 times. So in 19 out of 100 trials, we get a difference of 1.2, which is what happened in the actual experiment in this man's class. They got a difference of 1.2. And so how common is that to happen? 19% of the time. That's going to happen by accident, by like a fluke. For some reason, people's heart rates just went up for some reason, right? So there is a 19% chance that that's just going to happen by accident, okay? If I tell you that there's a 19% chance that it's going to rain outside, do you think it's going to rain? Probably not. So, like, is this a big deal that there's a 19% chance of this happening by chance? Maybe not, right? It's probably not that big of a deal, okay? So, probably the caffeine didn't make that big of a difference. Because the difference is somewhat likely to occur just by, you sitting there and your heart rate just decides to go up for some reason. Maybe you were thinking about something fun you did. Then this is not statistically significant. We don't have a statistically significant reason to think that the caffeine made any kind of a difference. It's going to happen 19% of the time just by you sitting there anyway, without any caffeine. So there's probably not a lot of statistical significance here. All right. Did we start this problem yesterday? I don't know. We'll just do it anyway. All right, so back to that distracted driving. Do you guys remember the distracted driving example? I mean, I know the 5 of you that weren't here don't remember, but all right. So here's the deal. We're going to have people drive in a simulator with either a passenger, and they're just going to be talking, or they're going to be driving while talking on a cell phone. And at the beginning of the experiment, they were told, hey, somewhere on the route, there's a rest stop. Make sure you stop, okay? So here's what happened. On the cell phone, people that were talking on the cell phone, 12 of them actually remembered to stop, and 12 of them forgot. They just kept on driving, okay? The people that had passengers in the car, 21 of them remembered to stop, and only 3 of them forgot, okay? So that is our data. So there were obviously 33 total remembered to stop, and 15 forgot out of the total of 48. So we want to look at the difference in the proportion of students who stopped at the rest stop in the 2 groups, passenger minus cell phone. I think I remember we did calculate this. Okay, so the passenger group. If we look at the passenger group, we had 21 out of the 24 in the passenger group that remembered to stop. Then, for the cell phone group, we had 12 out of 24 that remembered to stop. So what was the difference in remembering to stop between the two groups? Well, we just take 21 out of 24, and we take 12 out of 24, which is half, and we subtract them, and we get a difference of 0.375. Is that difference big enough to be statistically significant so that I can say that having a passenger versus having a cell phone is going to change whether or not I'm distracted? Well, that's where we do the simulation. So, we have this. Go. Here's a simulation of pretending to do this experiment 100 times. What does it mean if we get a difference of 0? What would that mean? There was no difference. That the passengers and the cell phone group stopped at the same rate, right? And if we get a difference of 0.1, passenger minus cell phone, that would mean that the passengers forgot, or they stopped more than the cell phone group. Okay, so the blue dot at 0.125, what does that dot represent? That is one trial in the simulation, okay? That blue dot is one trial in the simulation, and it got a result of 0.125. Now, what about our particular example? We had a difference of 0.375 it was, right? We had a difference of 0.375. How many times did that happen in the simulation? Well, that's 1.3. That never happened. So in the simulation, it would appear that that's not even possible to get a difference of 0.375 just by chance. Okay? So what that means here is that the difference of 0.375 or greater never occurred in the simulation. So that must mean that we had statistically significant results to prove that your distraction based on if you have a passenger versus a cell phone is different, okay? So have you guys ever, those of you who drive, do you think that there's a difference when you have a passengers versus if you're talking on the phone? Y'all don't ever talk on the phone when you drive, do you? Never, right? Oh, no, I don't do that. No, that's wrong. I get stopped by a cop for doing that. Oh, anyway, so do you feel that it's a difference? Like, do you feel like you're more distracted when you have passengers or when you're on a cell phone? Do you feel like one or the other is? What is it?
The phone's probably more.
You think the phone's more distracting? Why is that? Why do you think that? I mean, this is truly just your opinion. Why do you think the phone is more distracting?
Because you have to look at your phone.
You gotta look at the phone to see who you're calling, right? Okay, cool. What else?
Volume.
Oh, yeah, right? You turn up the volume. You're screaming at somebody, right? You're like, rah! And also, like, the person on the other side of the phone, they're not in the car with you. They might start an argument with you, and they don't care if you're going to, like, run into somebody because you're arguing with each other, right? Because they're fine. They're sitting at home on the couch screaming at you, and now you're driving mad. Have you ever driven mad? You drive different when you're mad than when you're happy. Did y'all know that? I'm just saying. Anyway, I digress. So there seems to be a difference because in a simulation, the results that we got never even happened. So obviously there's a difference, okay? That's what this shows us. Okay, cool. And then how unusual does the difference have to be? So we've seen two examples. We had the 19%. That didn't seem to be a big deal. That didn't seem to be a big difference. And then we had 0% chance that it was only by accident. That obviously is a big difference. So where do we draw the line? It's somewhere between 0 and 19%, okay? That's a pretty big spread. So usual versus not usual, somewhere between 0 and 19%. So I'm going to go ahead and give you guys I'm going to tell you a number. The number is 5%, okay? 5%. If something happens 5% by chance, then we call that kind of like, there's a 5% chance of something happening. Okay, well, that's good enough. But if it's less than 5%, then that means something must have made a difference. If you do something that has a less than 5% chance of happening, there was obviously something that made that difference happen. Okay, so we're going to go with 5%. 5% is our number. That's our cutoff on whether it's statistically significant or not. So if something happens that could only happen 5% of the time by chance, statistically significant, 5% or less. If it's more than 5%, it's probably not statistically significant. It could happen by chance anyway. That's our cutoff. All right, cool. And salmon. How many of you eat salmon? One person, two-ish. If my mom makes me, right? Here's some salmon and broccoli. Eat that. All right, cool. Well, apparently salmon has this cool thing called omega-3 that's very healthy for you. So fish oil, that's what a lot of people would use as a supplement. To see if fish oil helps to reduce blood pressure, males with high blood pressure were recruited and randomly assigned to different treatments. 7 of the men were randomly assigned to a 4-week diet that included fish oil. 7 other men were assigned to a 4-week diet that included a mixture of oils and that approximated the types of fat in a typical diet. So most people don't eat salmon very often, so they were having other kind of oil. At the end of the 4 weeks, each volunteer's blood pressure was measured again, and the reduction of their blood pressure was recorded. These reductions are shown in the table. Note that a negative value means that the subject's blood pressure actually went up, okay? So a negative number means that the blood pressure actually went up. So we need to outline a completely randomized design. That's drawing that tree diagram. We need to calculate the mean reduction for each group and find the difference. And then we're going to look at a simulation and decide if it was statistically significant or not. So let's do it. We're going to outline a completely randomized design. What do we start with? We're starting with what? 14 men. You got it. Whoops. That's the wrong thing. We're starting with 14 men. Perfect. Now, is it okay that all of the men had some kind of blood pressure issue? That's totally fine. Like, it's fine. It's no big deal. And it's fine that they're all men. So obviously we're looking at this particular study is talking about men who have blood pressure issues. Okay? And that's fine. But now what are we going to do with these 14 men? What should we do with them now? Perfect. We're going to randomly assign them. Random assignment. Cool. How many men go into each group? 7 men and 7 men. So we've randomly assigned them 7 men into each group. And we're going to give one group the fish oil and one group the other oils. Perfect. Awesome. Again, I randomly assign them. That reduces the bias. Do you guys remember what's the key phrase for random assignment? Why did I decide to randomly assign them? Yeah, I kind of heard. To create roughly equivalent groups. So hopefully some of the overweight men are in both groups. Hopefully some of the men that work out regularly are in both groups. So that I have kind of roughly equivalent groups happening. Okay, cool. And then at the end, I need to bring them back together and compare their blood pressure. We're going to compare their blood pressure, which is the response variable. All right, now we need to do some calculations. We need to calculate the mean reduction for each group and then the difference in the mean reduction. So I need the mean for the reduction of the fish oil. So the mean reduction of the fish oil. So the mean for fish oil. And then I need the mean of the reduction for the other, the mixture. You guys know how to find the mean, right? How do you find the mean? Roy says he knows. And you add them all up and divide by the number of numbers. Okay, cool. So let's add up 8, 12, 10, 14, 2, 0, and 0. 36, and then divide by 7. What is 36 divided by 7? Oh, is it 46? 20, 30, 44, 46. Yep, 46 divided by 7. What's 46 divided by 7? 6? 6.57. Okay, cool. And then now we're going to find the average for the mixture. So -6, negative matters. -6 plus 1 is -5 plus 2 is -3 plus -3 is -6 plus -4 is -2 plus 2 is -10. Is that right? Did I do that right? Did I do that wrong?
It was -10, we got to the -4,
Oh,
plus 2 would be -8.
Yeah. Oh, man. I'm glad the real math teacher's here. So what's the average? Or then we divide by 7. So what's the average for our mean mixture? I'm just plugging in a calculator. I don't know. -1 point what? 1.14. Perfect. Now I need to find the mean difference. So I'm going to take the fish oil, 6.57, and I'm going to subtract, oh, this is crazy, subtract the mixture, which is -1.14. What do you do when you subtract a negative? Let's go. So I'm going to add these up, and so that's going to be 7.71. Y'all didn't tell me that Miss Heater was a human calculator.
Yeah.
I love that.
Yes, Lindsay uses it all the time.
I love that, man. All right, so there's our difference. We got a difference in these groups of 7.71. Is that statistically significant?
No.
Well, we gotta look. So we got a mean difference of 7.71. Okay, so 7.71 would be like right here. This is where our difference was, 7.71. How many trials out of 100, I'm assuming there's 100 here? Yeah, probably. How many trials had 7.71 or more of a difference of only 2? So only 2 of 100, which is, what is 2 out of 100 as a percent? That's 2%. Only 2% happen by chance. So does it appear that we showed statistically significant results? Yes. That number is less than 5%, and so it appears we do have statistically significant results, okay? So we have statistically significant results. Okay, so that's all fine and good. But now let me ask you the real question that I care about. Did the fish oil actually make a difference in their blood pressure versus the regular oil? That's what this question, so if I tell you that there was statistically significant results between the fish oil group and the regular oil group, did the fish oil make an actual difference? Yes. Yes, it did. So this means that the fish oil actually made a difference, because this result would have only happened 2% of the time just by chance. Okay? So we have proven that you should have fish oil in your diet. Go eat salmon. Yay. All right, guys.